This is chapter 6, and this will be number 21 through number 44 for the conceptual problems. It says a 6 Newton falling object. So here's our object, and it's falling. It has a weight of 6 newtons, and we know that it encounters 6 newtons of force through air resistance. So we'll put that 6 newtons here. Because this one's going up, we'll make it positive. The other one is negative because it's going down, and if I add the two, I end up with a net force of 0 newtons. So it wanted to know what its net force was. For the next question, number 22, number 22 just says, girl pulls on a 10-kilogram wagon with a constant force of 20 newtons. They want to know what is the wagon's acceleration. So what we'll do here is we're going to take, here we're going to draw our girl. There she is, and she's going to pull the wagon here. And when she pulls the wagon, she pulls it with a constant force equal to 20 newtons. I know that force is equal to mass times acceleration. We know the force is 20. We know the mass of the wagon is 10. So we want to find the acceleration, and at this point we can do our math and find out the acceleration is 2 meters per second squared. Next one is number 23. So we'll go on to number 23. An object has a constant mass. So we know that the mass doesn't change. It says a constant force on the object produces constant acceleration. If this doesn't change, if mass doesn't change, and force doesn't change, then there's no way that our acceleration can change. So here, this is just constant acceleration. For number 24, it says if you pull horizontally on a desk with 150 newtons, so we're going to pull this way with 150 newtons, and we know that friction is moving in the opposite direction with 150 newtons, we say that it is not accelerating, so acceleration is 0, and there's not enough force to get it to move, so that's also 0 here. It says now you pull with 250 newtons, so the desk slides with a constant velocity. That's the key term here. They want to know what is the new frictional force. If it has a constant velocity, we know the acceleration is 0. We know that if I'm pulling with 250 newtons and the velocity is a number, but it's constant, the only thing we can do is say that friction has got to be the same because it cannot be accelerating. For number 25, it says you have a box. It's dragged, so we're going to drag it in this direction without any acceleration. So here we go again, no acceleration in a straight line path. The force pulling on it is 13 newtons. They want to know what's the frictional force. Well, remember, if there's no acceleration, the frictional force and the force that you're pulling with are going to be the same. So 13 Newton frictional force, and this will be the force of the pull, and it's also 13 newtons. So same thing once again. Number 26, a block is set at rest on an incline. So there's our incline, here's our block, and that block is attached to the, just sitting there on top of the ramp. It says the force of friction necessary to prevent the sliding increases when the angle is, so let's make the angle a little bit steeper, actually a lot steeper. And now we've got our box in there, and it's got, oops, that's kind of my box. And it's got the funny looking bottom on there, so we'll make a little bit better box here. It's a little hard to do on an incline. If I make it steeper, I know that here gravity is pulling it down, and I've got a normal force, remember, that's kind of coming down like this and then going across. On this one, the gravity is still the same length, but our normal force now is not very big at all in order to make that triangle. So here, when the angle goes up, so if the angle increases, then the force of friction also has to increase to keep that block from sliding. Next one is number 27. Suppose a force of friction on a sliding object is 25 newtons. So we're going to make the force of friction going this way, and it's 25 newtons. We said that's the force of friction, Ff. The force needed to maintain a constant velocity. So here we go again. Acceleration is 0 meters per second squared. So the force to get it to continue moving in that direction is also 25 newtons. We don't want an acceleration, but we do have a constant velocity. For number 28, you are on a frozen pond. The ice starts to crack. You lay down on the ice and begin to crawl so that you can make it to the other side. What this does, if you think about pressure, pressure is equal to force per unit area. If I have a force, let's say that I am 200 newtons, and the area that I am on is basically, let's just say 10 meters squared, then I know that the pressure here is going to be 2 newtons per meter squared, or 20 pascals. If I lay down, let's say that I go from 10 to, let's just say I go to 20 square meters, now my pressure is reduced down to 10 newtons per square meter. So here, this will decrease pressure. And that's the key for that one. So if you ever get stuck on the ice, that's what you need to do. For number 29, it says, which of the following would exert the most pressure on the ground? And the things that they give you is a lady with a shoe on. So here's her shoe, and that's the area of the shoe. We also have a ski, or a pair of skis. Oops, I went back the wrong way. We also have a pair of skis, and here's one of those skis. And here's the other one, so it also has a lot of area. And then finally we have the high heel, just the back of the high heel. So the back of the high heel is going to be really small like this. So it's going to have a lot of pressure. And that is what the answer is. It's just basically the high heel. And that has the most pressure. Let's go on to the next one. It says when a woman stands with 2 feet on a scale, scale reads 280 newtons. When she lifts 1 foot, what does the scale read? So let's go back and let's draw this lady. So here's our lady, and she's standing with 2 feet on the scale. She's got really little legs there, I guess. Here's her arms, here's her face, a little bit of hair, and she's standing on the scale, and it says 280. If she then takes one of her feet, so let's erase this foot, and we're going to make this foot kind of stick out to the side, and she's still standing on it, we know the pressure will go up, but her weight will stay the same. So this will just be, it stays the same. For number 31, it says pressure is defined as, and if you remember, pressure is just equal to force per unit area. That's really all there is to it for pressure. For the next one, we have the unit of pressure. We talked about 2 things. We said that it is a Newton per square meter, and that's also equal to a Pascal. And the Pascal is really the unit that you want to use. So we'll continue to try using the Pascal as we go through. For the next problem, let's go on to the next one. It is number 33. Aunt Minnie throws a rock downward. So this rock we're going to throw in a downward direction, and air resistance is negligible. That means that there is no air resistance, or so little we don't care, compared to a rock that is just dropped. So we're going to throw one rock, and we're going to drop another one. The acceleration of the rock after it is thrown, and actually it's the same. It is the same because it's just the acceleration due to gravity. The thrown one will take less time to hit the ground than the dropped one, but the acceleration is exactly the same. So we say that the acceleration is equal to the value for gravity. Number 34, a rock is thrown vertically. So now this time our rock is going up. At the very top of its trajectory, its net force on it is, well, we got to think about it. The only force that we have acting on the rock at the very top here, because its velocity is equal to 0, the only thing we have is just gravity. So gravity here is the only force acting on it. We know that mass times gravity is its weight. And because it has mass, the only force that's really working on it is, I'm going to go back here, is the weight of the object. Okay, let's go on. Number 35, it says a 10 kilogram brick and a 1 kilogram book are dropped in a vacuum. The force of gravity on the 10 kilogram brick is, so here we know that this is the mass of the brick times gravity, and it will be 100 newtons. Then the book, we have a force equal to 1 times 10, and that will be 10 newtons. So the brick is 10 times the force. So the force of gravity is 10 times the force of gravity than what it is on the book itself. Next one, an apple weighs 1 newton. The net force on the apple when it's in free fall is, we have to define free fall. Free fall means there is no air resistance. And because there's no air resistance, oops, T-A-N-C-E, no air resistance, the only force acting on the apple is the apple's weight. So here your answer would just be 1 newton. For number 37, a tennis ball and a solid steel ball, the same diameter dropped at the same time. The one that has the greater force is the one that has the bigger mass. So this one has a little mass, this one has a much bigger mass. And because we multiply both of those times gravity, we know the weight of the steel ball is much bigger than the weight of the tennis ball. For number 38, the reason the tennis ball and a solid steel ball will accelerate at the same rate, that means they both fall with a value of g. So the thing pulling each one of these down, the acceleration is just gravity. And that is why, the reason the tennis ball and the solid steel ball will accelerate at the same rate in the absence of resistance is just because that is the value for any falling object, regardless of its weight, regardless of its mass. The next one is number 39. And this one basically says when an object reaches its terminal velocity, its acceleration is equal to 0. And that's because the force pulling him down is the same as the force of the parachute pulling him up. So this is the same thing as this one. This one's negative. So we'll just put a little negative sign in there. But F minus F is going to give us no net force, which means that the acceleration is 0. The terminal speed for a person parachuting is about 15 kilometers per hour. 15 kilometers per hour. So it's pretty slow when you hit the ground, which is a good thing. Number 41, here's our bear. He's falling. He is the 20 Newton object, so I know that mg for him is 20 newtons. And the force of friction on his fur is 4 newtons. They want to know the magnitude of the net force. Here the net force will just be equal to the force, oops, since it's going down, we're going to put F of gravity minus F of air resistance. Force of gravity is 20, force air resistance is only 4, so the net force here is 16 newtons. For the next one, we've got a heavy person and a light person. They're parachuting together. So here's my heavy person. Here's my light person. They're a lot smaller. They have the same size parachute though, so you'll see that this parachute and this one are the same. They want to know which person hits the ground first. Well, because the heavier person has more mg pointing down than this one does, and we know that the arrows up represent the force of the air resistance, and these two are exactly the same because parachutes are the same size. This one has a bigger difference, so we know that the heavy person will reach the ground first. For number 43, a care package. Here you see several care packages. The velocity of those care packages right when they're dropped are 0, and then at 1 second they are 10 meters per second. And then at 2 seconds it'd be 20, but we know that gravity is the same at each point. So the acceleration stays the same. It does not change. So it's always G. And then number 44, which is the last one, a tennis ball and a solid steel ball with the same diameter dropped at the same time, so they're both falling. In the absence of resistance, which one has a greater acceleration? Remember, they both accelerate at G, so they would have exactly the same acceleration.